for the exam today. So what kind of calculus-based questions can you have? There are really three types. I have here one that I'm trying to illustrate, or two that I'm trying to illustrate with one picture. So the three types of things you could have would be, hello, Keela, would be calculating the center of mass of an object, integral of x dm over integral of dm, or finding the moment of inertia of an object, integral of r perpendicular squared dm, where dm, if it's one-dimensional for both of these, well, actually, x center mass is going to be one-dimensional, right? But lambda dx or sigma dA or rho dv, where lambda is equal to the mass divided by the length, but it's not necessarily a constant. You can have a varying mass per length. So I worked one example where we did a conical section so that if I did it as a one-dimensional problem, the mass per length was proportional to the length squared. Was length squared? No, actually, yeah. And sigma is the mass per area, and rho is the mass per volume. So that's one type of problem we could see. Next type of problem would be, well, actually that's two types. Type 1, type 2. And then the third type of problem would be the ones that involve liquids. Sorry, I just realized something. I marked Ashley in the wrong place. And so we had the pressure variation, d pressure is equal to rho g dx. When would we need to use this form of the equation? Okay, when it's in a fluid, but more importantly, when the density of the fluid changes. You have, for instance, we consider water to be non-compressible. So we say that the seawater density is the same no matter what your depth is. But that's not true. There's what we call a bulk modulus for water that tells you how the volume changes when you have a change in pressure. And so in truth, you're going to have the density depends on the pressure. So you have delta the delta pressure. That was put the wrong way. I'm trying to think of the bulk modulus is delta V is equal to V naught beta delta P. And so that's how the volume changes. So that means that the density is equal to mass over volume.
What happened to the beta in that equation?
To the what?
The beta.
It's right there. Does it not show up? Yeah, it shows up.
No, I mean like. Oh,
That's a bit.
That's a beta.
That looks like a B, but okay.
I didn't see it in the second formula. Oh no, you're just subbing.
This is a delta V for delta. Since V, this was, I should have put a V sub 0 here, plus delta V. And delta V is V0 beta delta P. And so that's the equation for the density. Doesn't get easy though, because delta P, the pressure change depends on the density. So it becomes a rather complicated little problem just to find what the actual density and pressure is as a function of depth, because they're interrelated. Obviously, I'm not going to give you that problem. I actually almost did, and I was like, no, that's a little much. Okay, so we also have dF is equal to pressure dA, d torque is equal to R cross dF. Those are the types of problems that we could have.
So the 3.
So I'm only going to put this 3 and 4 because I'm not going to do the dp equals rho g dx, just
So it's one of the.
one of those 4. So I have some examples here, and these examples are harder than the examples we did the first time because you've learned a little. Now I just realized I didn't give you any calculus problems in your homework sets. I really should have, right? To practice these skills that we saw in class. Otherwise you come to the test, you're like, oh, I only did it in my study time. I didn't have a homework problem to drill it in. So let's just look at this. How do I find the center of mass of a rod with a non-constant lineal density? Find the center mass. What's the first thing I got to do? What did you say, Ashley? Okay, I'm going to start with something more basic. Draw my picture. Well, there's lots of things to do. I'm not saying that your answer was not a good answer. So I have a picture here of it. And here I'm going to have x equals 0. Here x equals L. So I've got a figure. Then I have my equation. There. With those two things, I'm ready to roll. What do I replace my dm with? Lambda dx, and lambda is lambda sub 0 e to the minus x over L. I'm ready to work. You ready to do some integrals?
Wait, which? Sorry.
Go ahead.
Keep going. I'll find it here.
So for my integrals, I have x center mass is equal to the integral of x times lambda. Oh, I forgot my dx here. Is that what you were saying? I forgot the dx. I just put lambda. So of x lambda ought e to the minus x over L dx. What are my limits? From 0 to L. All divided by integral, again from 0 to L, lambda ought e to the minus x over L dx. Let's do the bottom integral first. What's the integral? Okay, lambda is a constant, so I can bring that out. Bring that on both top and bottom. What's the integral of e to the minus x over L dx? Of e to the minus x over L dx.
Minus L e to the negative x over L.
That's correct. Now, the way I think of this in my head is I know the fundamental theorem of calculus. Fundamental theorem of calculus is that the derivative of the antiderivative is the original function. That is, the derivative of the integral is your original function. So I know that the derivative of e to the minus x over L, you just bring down the derivative of the exponent, and that's the same. So when I integrate, I must divide by the derivative of the exponent and then repeat the exponent. So that's how I remember that integral. Well, on the top, it's a little harder. On the top, we have x e to the minus x over L dx. Integration by parts, if you don't have an integral table. So integration by parts, I would let u equal x and dv is equal to e to the minus x over L dx. Well, let's do it. I'm halfway through a problem and I can't just stop in the midpoint. It doesn't work for me. So there's my u and my x, therefore du equals dx. That's easy. And v equals the integral we just did. So now I'm able to do this integration by parts. It's uv, so it's going to be x times minus L e to the minus x over L from 0 to L. Minus the integral from 0 to L of v du So that top part gets more complicated and we go yay. But now it's a pretty easy integral, so let's finish it out. Notice those canceled. Not a problem. And then I'm going to have, putting in my limits on the top, for the green part, I'm going to have minus L squared. What's e to the minus 1? I don't know. Plus 0. So that's the first term, minus L squared e to the minus 1. And then the second term, minus and minus is a plus. But then, of course, when I do the integral, I'm going to get a minus L again, so it's going to be a minus. Did I do that all correctly? I believe I did, but I'm checking to see if anyone disagrees with that. Yeah. E to the 0 is 1, so that's why the second one, the e term is, well, there, e to the 0. Question?
Oh, no.
And on the bottom, putting in my limits, that's going to be minus L squared e to the minus 1 plus, wait, why did I say L squared? Minus L e to the minus 1 plus L e to the 0. Right, the only difference in this here and this one there is it's L squared on top and L on bottom. I'll cancel one L in each term. So I have e to the 0 minus 2 e to the minus 1 over e to the 0 minus e to the minus 1. And then we would have to put those in the calculator. E to the 0 is, of course, 1.
E to the 1. So e to the negative 1 is 0.3. 1.367.
Okay, so what's 1 minus 2 times 0.367? Oh, it's 0.2 something.
Yeah.
But it's 0.2 high something.
0.264.
0.264 divided by 1 minus e to the minus 1. So finally, decimal value. What was it?
Slightly to the left of the second.
So it's a little bit to the left, yes. So the center mass coming all the way over here if this is the midpoint, the center mass is somewhere around there. Because of the diminishing density as you go through the rod. So that's how you would calculate the center of mass if you have a changing lambda. Oddly enough, I did that on. No, I didn't do it on the line. I thought I'd done it right here. Okay, if I had a two-dimensional rectangular sheet of length L and width W, and my density is dependent on X and Y, as shown here. Now, this is a simpler integral by far, right? If I'm going to give you something that's variable, it's going to be something simpler, not something harder where you had to use integration by parts. So in this case, it doesn't tell you where the origin is in my wording here, which leaves it open to lots of different answers. But if we could assume for a moment that the density is never going to be negative, then the origin is going to have to be either at the corner or outside of the object. So I intended for this to have the origin like this. In which case you're going to have x center mass is equal to the integral of x
Integral, like, I mean, not integral, d area.
Yes, d area.
Is dx dy?
Yeah, d area is dx dy. Sorry, I should have pointed that out, yes. For simple rectangular coordinates, d area is dx dy.
So how do you, so that means that you have to integrate twice?
Yeah, so that means I have a little piece here that has a width of dx in this direction.
Right, does that mean it's a double integral?
Yes.
Okay.
So we sometimes will write our integrals like this, probably because we're lazy. Obviously, if you're going to put the limits, you have to put the second one. And so our x is going to go from 0 to, did I give dimensions? 0 to, which one's the length? Well, let's not worry about it. Let's just say that the length goes with y. So now we have these two integrals, but w only depends on the integral of, or excuse me, x only depends on the integral of, oh man, I want to speak English someday. The integral with respect to x, y doesn't care about that. I can move the y through the integral with respect to x, or x through the integral with respect to y. So I can break these up into two separate integrals on top and bottom. Sigma can come through everything because it's a constant. And then I'll have integral from 0 to L of y dy, integral from 0 to L of y dy, and then integral from 0 to W x squared dx, integral from 0 to W of x dx. Now, what do you see immediately? The sigmas cancel. The y integrals cancel because they're exactly the same thing. And so I just have to do the red integrals. And so integral of x squared dx is x cubed over 3. And integral of x is, as Corso said, put in your limits.
should ask us this one.
I should ask you this one?
Yeah.
It's already written, so you're not going to affect me.
Remember last time how you said, how you asked us the one we did at the very end? How was the pattern this time? Instead of telling us next Tuesday, you tell us today. It was Tuesdays, you don't have.
I like your sense of humor. Trace needs a commitment on this one. Okay, so there's an example of two-dimensional with I just did the X, but what would you get if you did the Y calculation? Yeah, given the symmetry, right there's complete symmetry between the X and the Y. So it's, the Y center mass is going to be 2/3 L.
I have a question.
Yes.
Why do you have X squared on top and then X on the bottom?
Where? What are you talking about in this one?
I just don't know the X.
Okay, it's because for the center of mass, the
Oh,
equation
I
is
see.
X center mass is equal to. It's I know you said you see it, but I can't stop halfway
Oh,
through.
that's fine.
So it's because of this X right here.
Okay, that makes more sense.
Okay, so it'd be a waste of time to do the next one. And then we have a sphere of radius r with a changing density. Now, next semester, we're going to do problems with charge density. And I believe one of the problems you're going to have to do right off the bat is this integral. So when you have a spherical symmetry, what's the first thing that comes to mind for, ruh-roh, that's harder than I expected? Okay, maybe it's not harder than you expected. The first thing is, because it has spherical symmetry, you're going to want to use the spherical coordinate system. Right? If it has spherical symmetry, it's going to be easier in the spherical coordinate system. If I did this in the Cartesian coordinate system, my r would be square root of x squared plus y squared plus z squared. And then when I start doing my integrals, dx, dy, dz, it starts becoming complicated. So it's easier to shift it over to the spherical coordinates. And so, of course, I have a sphere. Here's my origin. And I have my angle like this, which my angle from here down trying to do it like that, and the radius r is this length. And I know I can't draw three-dimensional to save my life. dv is equal to r squared sine theta dr d theta d phi. And so given that, I want to find the center of mass, really? How do you find the center of mass in this case? Because it's spherically symmetric, it's going to be in the middle. Now, the problem, so you could answer this without doing any calculus. You could say, because of the spherical symmetry, it's in the middle.
And it'd be right.
It would be right. The question that I gave you on the exam, which is not this question, can be solved without doing calculus. But I specified the problem, you must do it the calculus way. So you have to do it that way to get credit. So obviously I give you the answer. You don't need to check your answer by doing it the non-calculus way. To get credit, you're going to need to do it the calculus way. So how would I do this the calculus way? Well, I would need to define x in terms of r, theta, and phi. Now, we went through this in class, but there's a good chance you don't remember. So let's do Z. Z is the easy one. Z is the vertical part. And so if we have a radius r and an angle from the vertical axis of theta, then Z is just the adjacent side of a right triangle. Here's the Z, here's r, here's theta. And so Z is equal to r cosine theta. Now, the length of this piece is r sine theta. And so x is going to be this portion here, which would be adjacent to phi. So that's r sine theta cosine phi, and y, no, bad color. Y is this side, which is r sine theta sine phi. So now we could find the center of mass coordinates, and, you know, like I said, the Z one is the easy one. So Z center of mass is equal to integral, triple integral, right? Of, that's not, Z is r cosine theta. Oh. Go ahead.
Whenever you're done writing that, can we hop back and see where I got the x and y coordinates? We must have missed them. So I get where you got z, but then I don't get where you got x and y.
Okay, so looking at this triangle right here, the z, and then this is, I'll put xy, well, square root of x squared plus y squared is what this one has to be, because that's the component in the xy plane. It's this piece right there, is that side of the triangle. So that's the opposite side. So I'm going to have sine theta. Our sine theta is the length in the xy plane. And then since that angle phi was defined from the x-axis, I take the length in the xy plane times cosine of that angle phi to get the x component. Right, so let me draw the second triangle now. So the second triangle has angle phi. This side here is r sine theta. This is x and this is y. And so x is the adjacent side to the angle. And so x is equal to the hypotenuse times cosine of my angle. And y is the opposite side, so it's equal to the hypotenuse times the sine of my angle. Verstehen Wakarimasu ka?
I'm just trying to. So that second triangle is where?
That second triangle is in the xy plane.
Can you figure out that the hypotenuse is r sine theta
Because that was from the first triangle. This first triangle, z was the vertical, and then the opposite side was the length in the xy plane. Right? Because you have xyz, you have the z, and then whatever it is in direction perpendicular to that, which is the xy plane.
Okay, I think again.
Okay. Now this looks like it's going to be not your most pleasant of integrals, but we can short circuit the whole thing by realizing this is equal to the integral of cosine theta sine theta from 0 to pi, come on, d theta times the integral from 0 to 2 pi d phi times the integral from 0 to r of r cubed e to the minus r over r dr times the constant that I forgot to write, rho 0. So I have 3 separate integrals on top. On the bottom, I'm going to have this. Well, why is this easy? The integral of cosine theta sine theta. Integral of cosine theta sine theta, we can actually do a u substitution. Let's let u equal, I'm trying to think of the way to make this so it comes out easier looking. I will let u equal cosine theta. And so what is du?
No, sine.
It's going to, du is going to be minus sine. So if I put that together, that integral becomes the integral from cosine of 0 is 1, cosine of pi is minus 1, so integral from 1 to minus 1 of minus u du. Which is? Which is 0. I don't need to do any of the other integrals here because that one came to 0. And then I can say, I've done some calculus. The choice of z direction was completely arbitrary. Hence, it has to be 0 in all directions. Yeah.
On the first integral of the bottom of the fraction, is that sine theta?
Yes, that's integral of sine theta d theta.
Okay, that's what-
That comes from the dv, right? The
Yeah.
dv has.
No, I just couldn't actually read it.
Couldn't actually read it. Sorry. So we found the center of mass. Now, the moment of inertia. How would I find the moments of inertia?
Which one?
Okay, I found the centers of mass. Now it says find the moment of inertia about the center of mass. You have to find the center of mass before you can find the moment of inertia, right? About the center of mass. So how do I find the moment of inertia now?
It's different for every sheet.
Well, but the equation that we use to calculate it is not different for every shape.
Oh, L.
The- Right here. So I need to identify the R perpendicular. The DMs are going to be the same as before. And then I'm going to integrate over my specified limits. So because I only have 14 minutes left, I want to get on to the second part. I don't want to do all of these calculations again. But like for the first one, I found my center mass is this 0.418 L. And so I would have my integral going from minus 0.418 L to, well, no, I better not do that. I better keep it going from 0 to L. But I'm going to have my R perpendicular is equal to x minus 0.418 L. Because if L is 0, it's over to the left. And if L is L, it's over to the right by that value. And so then I'd have the R perpendicular squared times the dm, which in this case was not sigma, lambda. And so I have to do that integral. To do the integral, you've got that square. And so there's more than one way to skin the cat. The most straightforward way, probably not the easiest, probably the easiest is to say, let u equal x minus this, and write e equals minus x over L to be e equals something that has a u, and have that will give you a constant times a variable. But the most straightforward way is to just multiply out that square. So you have one term that's x squared e to the minus x over O, one that's x e to the minus x over O, and one that's constant e to the minus x over O, and do those three integrals separately. Once again, it's going to kind of be long, right? But you just solve that integral. That's how you'd find the moment of inertia, that one. Now the next one, the rectangular sheet, we found that's center of mass. We once again need to find what the axis we're going to rotate about is. I didn't say what the axis is. I just said about the moment of inertia. Let's assume that it's an axis coming straight out of the sheet. So it's doing a flat spin. It's going like this. Right. Going like this about the center mass. And so then we would have the R perpendicular is going to be the distance from the center mass. Let's see, it was 2/3. So the center mass is 2/3, so it's right about here. And I would have R perpendicular is going to be x minus x center mass squared plus y minus y center mass squared is equal. That's the Pythagorean theorem. R squared is equal to x squared plus y squared. But I have to center it on the center of mass. So now that I have R perpendicular squared, I put that into my integral, and I have so there's my R perpendicular squared. And then I have to put in my and I go and do that integral. That one is not so difficult, but it has a double integral. You have to do one first, then the other. Doesn't matter which one you choose first. So, you expand out the x minus 2/3 w squared. So you have an x squared term, an x squared, and a constant. In terms of x, the y thing is all a constant. All times x dx. Do that, then do the integral for y, and you get your answer. Got a question, Alex?
Will those dm equations, dm equals lambda dx and stuff like that, will that be on our equation sheet?
Yeah, at least I think it is. I'll double check. Okay, and the sphere, I only have 9 minutes now, so I'm not going to work on the sphere one. Let's go to what we did last week. Last week was when we looked at the force and torque calculations for water on a dam. So last week we had a fairly complicated system, right? We had a system where the dam was, that's not a vertical line. It had a vertical wall, then it had a slope, had a little slope, had a bigger slope. Right, it was a reasonably complicated thing. I'm not going to give you something complicated like that. I want to make that real, right? That was a real dam we did the calculations for last week. So let's try something that's a lot simpler. Let's just say that we have a bluff dam. Has a vertical wall here. And I have water. And of course, it's completely filled. They try not to do that in reservoirs, right? But it's completely filled. We have some height h. And there's some width here that would just be specified w. And we ask, bad job. We ask, what's the total force pushing the dam to the right? If I ask you for the total force pushing the dam to the right, how do you answer?
All the sum of all the pressures. So it'd be like the integral of pressures over the distance. So.
Okay, you're absolutely right. So I'm going to take a little piece that will have height dy and width of w. So if I look at it sideways, it's a long slit like this with a height of dy and a width of w. Right, so that's my slice. And on that slice, I'm going to have a force due to water pressure. Remember, water pressure, any pressure is always compressive. It's always pushing directly in on the surface. So I'm going to have a dF that's equal to the pressure times dy. Not pressure times dy, times d area. Pressure times d area, because pressure is force over area. Force, pressure times area. So pressure times d area. Well, what's the d area for this slit? W dy, right? It's a rectangle. W one direction, dy the other. So dA is W dy. One-dimensional integral, even though it's a two-dimensional surface. And so now we just have to say, following what Alex said, the force is equal to the integral of dF going from top to bottom. It's integral pressure dA. Well, pressure is equal to rho of our fluid times G times the depth. So there's pressure, W dy. Now, one thing I didn't put in here, I didn't put in atmospheric pressure. I didn't put in absolute pressure. I said, what's the total force caused by the water? So the total pressure is not just the rho gy, is it? It's got the pressure that's at the top of the dam, which would be atmospheric pressure. So let's, I think I missed something. Yep, missed something. So pressure atmosphere plus now I just need to put in my limits. What direction is positive in this problem? Down. Now, that's not the answer anyone expects, right? Because in physics, we always use up as positive. Alex just answered, that's the way we do it. But the pressure is getting greater as I go down, and I put rho gy. So if rho gy gets larger with y increasing, then down is positive in this case. So it's really important to pay attention to that kind of thing. And so I'm going to go from 0 to h for my limits. So here is my origin 0, 0, and y is going positive down. Well, we can do this. This is two separate integrals. One is pressure atmosphere times width times the integral from 0 to h dy. The other is rho fluid g width integral from 0 to h of y dy. Those are both easy integrals, aren't they? Everybody nod your head. Those are both easy integrals. So there you have it. That's the total pressure that's pushing on the dam due to the water. But a lot of people would say that first term was unnecessary because if you look at the dam on the backside, the pressure is just essentially constant air pressure all the way. Yes, air pressure does get slightly bigger as you go down, but the density of air is really small. And because the density of air is really small, it's virtually constant. And so that first term is also going to tell us the force of the air pressure pushing back against the other side. So the net force due to the water is the second term. The first term is adding in the atmospheric pressure, which is actually pushing both sides equal. So I am now out of time.
What would you say concept for the?
The concept for this one? The concept would be that the force is pressure times area, and because the pressure is changing with depth, I have to integrate over the height of the dam. Yeah.
Why do we not worry about the change in width?
The what?
The change in width.
Okay, why do we not worry about the change in width for the net force? Or, well, not width, but since I called width another dimension, but I know what you mean. You mean, why are we not worried about this distance here being small and this distance here being large? Okay, and the reason is, if you look at that back side, this is a really good question. If you look at the back side, the force is always going directly in, right? Okay, those are supposed to be normal in all cases. And so for each one, you'd have to break it into what's the vertical component, what's the horizontal component. And as you do that, what you find mathematically is that for the horizontal parts of the force, it's the same as if you had that constant pressure pushing over just the vertical aspect. And for the vertical portion, it's as if you had that, because you're breaking each vector into components and adding them up, the length here is much bigger than the length of the vertical or the length of the horizontal. And so, you know, I'm not doing the math here because you have to choose a shape and you can prove it for that shape. And then you say, well, it's for that shape. What about another? And you know, you can get there and show a general proof, but it's a lot more than 0 minutes worth of time to show the general proof. But that's why. So you just, all you need to look at is the area seen from the direction you want times the pressure. But that is a really good question because obviously it's more complicated in doing the math without knowing that. All right, I'll see you in an hour and a half.